welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 659, titled Split Array into Consecutive Subsequences. In this session, we'll explore the problem statement, dive into possible approaches, and analyze their complexities. Let's get started. In this problem, you're given an integer array nums that's already sorted in non-decreasing order. The goal is to determine if it's possible to split this array into one or more subsequences that meet two specific conditions. First, each subsequence must consist of consecutive integers, meaning the numbers must follow each other without any gaps, like 1, 2, 3. Sequences like 1, 3, 4, where there's a gap, are not allowed. Second, each subsequence must have a minimum length of 3. For example, 1, 2, 3 is valid because it meets both conditions, but 1, 2 is invalid because it's too short. Based on these rules, you need to return a Boolean value, true if it's possible to split the array into valid subsequences, and false otherwise. Let's look at some examples to understand this better. In the first example, the input array is 1, 2, 3, 3, 4, 5. The output is true because we can split this array into two subsequences, 1, 2, 3, and 3, 4, 5. Both of these are valid since they consist of consecutive integers and have a length of at least 3. This means the conditions for a valid split are satisfied, so we return true. In the second example, the input array is 1, 2, 3, 3, 4, 4, 5, 5. Here, the output is also true, and we can split the array into three subsequences, 1, 2, 3, 3, 4, 5, and 4, 5. The first two subsequences are valid because they meet both conditions. The third subsequence, 4, 5, is too short to be valid on its own, but the first two subsequences ensure that all numbers are accounted for in valid groups. This satisfies the requirements, so the result is true. In the third example, the input array is 1, 2, 3, 4, 4, 5. The output here is false, because it's impossible to split the array into subsequences that meet all the conditions. For instance, splitting into 1, 2, 3, and 4, 4, 5 doesn't work because the second group contains duplicate 4s and isn't made up of consecutive integers. No matter how you try to split the array, you'll encounter issues that violate the rules. The constraints of the problem, such as the array length and the need for consecutive integers, make certain edge cases important. For example, arrays that are too short, have all identical elements, or include gaps between numbers are prime examples where a valid split might not be possible. To solve the problem of splitting an array into consecutive subsequences, let's first consider the brute force approach. The intuition here is to generate all possible subsequences and verify if they meet the criteria of being consecutive and at least length 3. To achieve this, we can use recursion or backtracking to form all subsequences, check each one for validity, and confirm that all elements of the array are used in valid subsequences. However, this method is computationally expensive, with a time complexity of O(2 to the power of n, due to the exponential growth of possible subsequences as the input size increases. Additionally, the space complexity is O(n), because of the recursion stack. While this approach is simple to understand and implement, it becomes impractical for large input sizes, such as when n equals 10,000, due to its inefficiency. A more efficient strategy is the greedy approach, where we aim to extend existing subsequences whenever possible, rather than starting new ones unnecessarily. The key idea is to use greedy logic to append a number to an existing subsequence if it fits, or start a new subsequence only if no extension is possible. To implement this, we rely on two hash maps, one called frequency to track the frequency of each number in the array, and another called append_frequency to record how many subsequences can accept a specific number as their next element. We begin by populating the frequency map with the count of all numbers. Then, as we iterate through the array, we attempt to either extend an existing subsequence using append_frequency or start a new one if the frequency map allows it. If neither option works for a given number, the solution is invalid, and we return false. If we successfully process all numbers, the output is true. The greedy approach is particularly appealing due to its efficiency. Its time complexity is O(n), as each number in the array is processed at most twice, once when it is added to a subsequence and potentially a second time when its frequency is updated. The space complexity is also O(n), attributed to the hash maps used for tracking frequencies. While this solution is optimal, it does require careful implementation to manage the hash maps effectively. An alternative solution uses a heap-based approach, which is conceptually similar to the greedy method but relies on a priority queue to track the lengths of subsequences. For each number, the heap is checked to see if the subsequence can be extended, and it ensures all subsequences in the heap are at least length 3. However, this method has a higher time complexity of n log k, where k is the number of unique numbers, and involves additional memory overhead for managing heaps. Although easier to implement, it is slower compared to the hash map-based greedy approach. Among the approaches considered, we chose the greedy strategy with hash maps as the most efficient and well-suited solution for this problem. The main advantage lies in leveraging the frequency map to track the remaining numbers and the append_frequency map to quickly determine whether a number can extend an existing subsequence. This design avoids the computational overhead of generating all possible subsequences, as seen in the brute force method, and the repeated heap management required in the alternative approach. The greedy method achieves n time complexity, making it optimal for processing large inputs. Furthermore, hash maps allow for fast lookups and updates, ensuring that the solution scales well with input size. While slightly more complex than brute force, this approach is practical, avoids unnecessary computations, and strikes an excellent balance between efficiency and simplicity. When comparing the approaches, the brute force method is clearly impractical due to its exponential time complexity of 2 to the power of n, which quickly becomes infeasible for larger inputs. The heap-based approach is a viable alternative but comes with a slower time complexity of n log k, and requires additional memory for managing heaps. In contrast, the greedy approach proves to be optimal with its linear time complexity of n, and space complexity of n, provided the hash maps are carefully managed. This balance of speed, memory usage, and clarity makes the greedy solution the superior choice. By avoiding unnecessary computations and leveraging efficient data structures, it ensures the problem is solved effectively, even for large-scale inputs. To solve this problem, our goal is to identify all valid subsequences of an array where each subsequence has a length of at least 3 and consists of consecutive integers. This means we're looking for groups of numbers that form a sequence like 1, 2, 3 or -1, 0, 1. If the input array has fewer than 3 elements, it's impossible to form such subsequences, so we can immediately return an empty list. The first step in the brute force approach is to handle the input. We start by reading the array ARR of size n. If n is less than 3, we exit early, as no further computation is needed. This simple check ensures that we avoid unnecessary processing and sets the stage for generating subsequences when the input size is sufficient. Once we've confirmed the input is large enough, the next step is to generate all possible subsequences of the array. There are two main techniques for doing this: recursion and bitmasking. Using recursion, we start with an empty list and, for each index in the array, decide whether to include the current element in the subsequence or skip it. This process continues until all indices are processed, resulting in the generation of all possible subsequences. Alternatively, bitmasking involves treating each element of the array as a bit in a binary number. By iterating through all binary numbers from 0 to 2 to the power of n1, we can systematically include or exclude elements based on the state of each bit. After generating the subsequences, the next step is to filter them to find the valid ones. A valid subsequence must have a length of at least 3, be sorted in ascending order, and consist of consecutive integers. Sorting ensures that we can easily check for consecutive numbers, and if these conditions are met, we add the subsequence to the result list. Finally, we return the list of all valid subsequences. The brute force approach we've described has some key characteristics and challenges. First, generating all subsequences has a time complexity of 2 to the power of n, as there are 2 to the power of n possible subsets for an array of size n. Filtering each subsequence adds extra complexity, as it involves sorting, which takes k*log k, for a subsequence of length k. This exponential growth makes the approach infeasible for large inputs. Sorting is essential because subsequences can be generated in any order, and we need the elements to be in ascending order to check for consecutiveness. Without sorting, the validation step would become much more complex. To improve this approach, we can apply certain optimizations. For example, we can enforce constraints during subsequence generation, such as only including elements that maintain consecutiveness, to reduce the number of invalid subsequences. Additionally, early stopping in recursion can help avoid unnecessary exploration when it's clear that a subsequence cannot meet the criteria. Now let's discuss the data structures that support our algorithm. We use lists to store subsequences due to their dynamic resizing capabilities and the ease of appending elements. For validation, a hash set can be used to ensure that the result contains only unique subsequences, avoiding duplicates. Handling edge cases is also critical for a robust solution. If the input array is empty, we return an empty list, as there are no elements to form subsequences. Similarly, if all elements in the array are identical or too far apart to form consecutive sequences, the output will also be empty. Another consideration is mixed positive and negative numbers. Sorting and difference calculations should work seamlessly regardless of whether the numbers in the array are positive, negative, or a combination of both. This ensures that the algorithm is general and handles all possible inputs correctly. Finally, we need to address how duplicates in the input array are handled. Duplicate values can lead to redundant subsequences being generated, which may inflate the result unnecessarily. To avoid this, we can leverage a hash set to store unique subsequences, ensuring that duplicates are automatically removed. Alternatively, during subsequence generation, we can skip over duplicate elements under specific conditions to prevent redundant combinations from being explored in the first place. Handling duplicates effectively is crucial for maintaining the correctness and efficiency of the algorithm, especially when the input contains repeated values. Here, we start by importing the necessary modules, counter from the collections module to count the frequency of elements in the array, and defaultDict to handle default values for appending frequencies. Inside the isPossible method, we first calculate the frequency of each number in the input list nums using counter. This gives us a dictionary where the keys are the numbers and the values are their counts. Next, we define another dictionary called append_frequency using defaultDict to track the numbers that can extend existing subsequences. Now, we begin iterating through each number in the nums list. If the current number has already been used up, indicated by its frequency and frequency being 0, we skip it and move to the next iteration. If the number can be appended to an existing subsequence, we reduce its count in append_frequency and increment the count for the next number in the subsequence, since the sequence now extends to include that next number. If appending is not possible, we then check if we can start a new subsequence starting with the current number. For this, we ensure that the next two consecutive numbers also exist by checking their frequencies in frequency. If they do, we decrement their frequencies and update append_frequency to reflect the new subsequence ending at the third number. If neither appending to an existing sequence nor starting a new one is possible, the function will eventually return false because the condition for forming consecutive subsequences cannot be met. In this part of the implementation, the function returns false as soon as it encounters a situation where the current number cannot be used in any valid way, either by appending to an existing subsequence or starting a new one. Otherwise, if the number is successfully used, its frequency and frequency is decrement to reflect that it has been processed. Once all numbers in the list are processed without hitting an invalid condition, the function returns true, indicating that it is indeed possible to split the array into one or more subsequences where each subsequence consists of consecutive integers and has a minimum length of 3. This ensures that the function can handle the input efficiently while maintaining the constraints of the problem. In this Java implementation, we start by importing the necessary utilities and defining our solution class. The core function here is isPossible, which takes an array of integers as input. To solve the problem, we use two hash maps. The first map, frequency, keeps track of the frequency of each number in the input array, helping us know how many times each number is available. The second map, append frequency, helps us track the number of subsequences that can potentially end at a given number. This is crucial for efficiently determining whether a number can extend an existing subsequence. The first loop populates the frequency map by iterating over the input array and counting occurrences of each number. Once that is done, we move to the main logic. For each number in the array, we first check if its frequency is 0, meaning it has already been used in a subsequence. If so, we skip it and continue. Next, we check if the current number can be appended to an existing subsequence by verifying if append frequency contains it as a valid key with a positive value. If this condition is met, we decrement the count for the current number in append frequency and increment the count for the next number, allowing the subsequence to extend. If appending is not possible, we attempt to create a new subsequence starting with the current number. This requires that the next two consecutive numbers are also available in the frequency map. If they are, we decrement their frequencies to mark them as used and reserve space in append frequency for the number that comes after the new subsequence. Here, we complete the logic for forming new subsequences or identifying when it's not possible. If a new subsequence is successfully started, we update append frequency to indicate that the subsequence can end at the number 3 steps ahead, ensuring that future numbers can extend it. However, if neither appending to an existing subsequence nor creating a new subsequence is possible, we return false, as this means the array cannot be split into valid subsequences. Finally, at the end of the loop, we decrement the frequency of the current number in the frequency map to reflect that it has been used, ensuring it won't be reused incorrectly later. If the entire loop completes without returning false, it means all numbers in the array were successfully processed into valid subsequences. In that case, we return true. This approach efficiently manages the subsequences using the two hash maps and ensures that the solution adheres to the problem constraints. In this example, we are given the array 1, 2, 3, 3, 4, 5. First, we initialize two data structures. The frequency dictionary counts the frequency of each number in the array, resulting in 1, 1, 2, 1, 3, 2, 4, 1, 5, 1. The append_frequency dictionary, which tracks subsequences that can be extended, starts as empty. Now, we begin processing each number in the array. Starting with the number 1, we see that frequency 1, 0, meaning it is available. Since there is no existing subsequence ending at 1, append_frequency 1 == 0, we check if we can start a new subsequence. Both 2 and 3 are available in frequency, so we use 1, 2, and 3 to form a new subsequence. This updates frequency to 1 o'clock, 2 o'clock, 3, 1, 4, 1, 5, 1, and append_frequency to 4, 1, indicating a subsequence ending at 4. Next, when processing the number 2, we find frequent 2 == 0, meaning it has already been used, so we skip it. When we process the number 3, we see that frequency 3, 0, meaning it is still available. There is no existing subsequence ending at 3, append_frequency 3 == 0, so we check if we can start a new subsequence. Both 4 and 5 are available in frequency, so we use 3, 4, and 5 to form another subsequence. This updates frequency to 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, and append_frequency to 4, 1, 6, 1, indicating subsequences ending at 4 and 6. For the numbers 4 and 5, we find that frequency 4 == 0 and frequency 5 == 0, meaning they have already been used, so we skip them. Since all numbers have been processed successfully, we return true, indicating that the input array can indeed be split into consecutive subsequences. In this example, the array is 1, 2, 3, 4, 4, 5. We start by initializing our data structures. The frequency dictionary counts the occurrences of each number, resulting in 1, 1, 2, 1, 3, 1, 4, 2, 5, 1, and append_frequency is initialized as an empty dictionary. Processing begins with the number 1. Since frequency 1, 0, it is available. There is no subsequence ending at 1, append_frequency 1 == 0, but we can start a new subsequence since 2 and 3 are both available. Using these numbers updates frequency to 1 o'clock, 2 o'clock, 3 o'clock, 4, 2, 5, 1, and append_frequency to 4, 1, indicating a new subsequence ending at 4. For the numbers 2 and 3, frequency 2 == 0 and frequency 3 == 0, so we skip them, as they have already been used. Next, we process the number 4. Since frequency 4, 0, it is available. We can extend an existing subsequence ending at 4 because append_frequency 4, 0. Extending this subsequence decrements frequency 4 to 1, updates frequency to 1 o'clock, 2 o'clock, 3 o'clock, 4, 1, 5, 1, and adjusts append_frequency to 4 o'clock, 5, 1, indicating that the subsequence now ends at 5. Processing the number 4 again, we see that frequency 4, 0, so it is available. However, we cannot extend any existing subsequence since append_frequency 4 equals 0. Additionally, we cannot start a new subsequence because both 5 and 6 are not available in frequency. Thus, at this point, it is impossible to split the array into consecutive subsequences, and we return false. In this example, the array is 1, 2, 3, 4, 5, 6, 7, 8. We start by initializing the frequency dictionary, which counts the occurrences of each number, resulting in 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, and append_frequency starts as an empty dictionary. Processing begins with the number 1. Since 2 and 3 are available in frequency, we can start a new subsequence using these numbers. This updates frequency to 1 o'clock, 2 o'clock, 3 o'clock, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, and append_frequency to 4, 1, indicating a subsequence ending at 4. For the numbers 2 and 3, frequency 2 equals 0 and frequency 3 equals 0, so they are skipped since they have already been used. When processing the number 4, we see that it can extend the existing subsequence ending at 4 because append_frequency 4, 0. Extending this subsequence updates frequency to 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6, 1, 7, 1, 8, 1, and append_frequency to 5, 1, indicating the subsequence now ends at 5. We continue this process for the remaining numbers, extending subsequences wherever possible, and updating frequency and append_frequency accordingly. By the end, all numbers are used, and frequency becomes empty. Since all numbers are successfully processed into consecutive subsequences, we return true. In this algorithm, the overall time complexity is O(n), where n is the length of the input array nums. Let's break this down step by step. First, we initialize the frequency count using Python's counter from the collections module. This step involves iterating through the entire array once, which takes O(n) time. Next, we process each number in the main loop. For every number, we perform a constant amount of work, such as checking conditions, updating the dictionaries, and decrementing counts. Since each number is handled only once before its frequency is reduced to 0, the total work in this step is also O(n). Additionally, the dictionary operations, like lookups and updates for frequency and append_frequency, are O(1) on average due to the efficiency of Python dictionaries. Combining these steps, we see that the algorithm processes the array in linear time. When we add up the contributions from the frequency initialization, main loop processing, and dictionary operations, the total time complexity remains O(n) plus O(n), which simplifies to O(n). Now, let's analyze the space complexity. The solution uses two main dictionaries, frequency and append_frequency. The frequency dictionary stores the frequency of each number, and in the worst case, when all numbers in nums are unique, its size is O(n). Similarly, the append_frequency dictionary tracks where subsequences can be extended. In the worst case, if every number is part of a unique subsequence, its size will also be O(n). Additionally, the input array nums itself takes up O(n) space. When we combine these factors, the total space complexity is O(n). To better understand the algorithm's performance, let's examine the best, average, and worst cases. In the best case, all numbers in nums extend existing subsequences, so no new subsequences need to be created. Even then, the algorithm processes each number once, resulting in O(n) time complexity. In the average case, some numbers extend existing subsequences while others require new ones. Despite this mix, the algorithm still performs constant time dictionary operations and processes each number once, maintaining O(n) time complexity. In the worst case, every number in nums forms a new subsequence. Even under these conditions, the algorithm handles each number only once, leading to O(n) time complexity. This consistent efficiency highlights the robustness of the solution. Let's compare this optimized approach to a brute force solution. A naive method would involve generating all possible subsequences and checking their validity. This would result in an exponential time complexity of O(2 to the power of n, which is impractical for large inputs. In contrast, the optimized solution leverages greedy techniques and efficient dictionary operations to track frequencies and subsequences. By processing each number at most once, this approach achieves a significantly better time complexity of O(n). Mathematically, this is because the total work is proportional to the size of the input array, and dictionary operations are constant time on average. The space usage is similarly efficient, dominated by the dictionary's frequency and append_frequency, each of which grows linearly with the size of the input. Thus, both the time and space complexities of the optimized solution are O(n), making it well suited for this problem. When working on this problem, one common mistake is confusing subsequences with subarrays. Remember, a subsequence does not require elements to be contiguous, while a subarray does. Misunderstanding this distinction can lead to overly restrictive or incorrect solutions, so it's helpful to review the definitions and use examples to clarify. Another area where errors arise is relying on brute force solutions without optimization. While brute force may seem like the intuitive starting point, it can quickly become computationally expensive, especially with larger inputs. For instance, generating all subsequences can result in exponential time complexity, which is impractical. Instead, focus on identifying patterns or leveraging dynamic programming to reduce the solution space. Lastly, overlooking edge cases is a frequent issue. Scenarios like empty arrays, arrays with a single element, or arrays with all identical elements should always be considered. Explicitly testing these during development can prevent runtime errors and ensure your solution is robust. Another challenge developers face is the incorrect use of recursion or backtracking. For example, missing base cases or improperly managing return values can lead to stack overflow errors or infinite recursion. To address this, carefully design your recursion tree and validate it with small examples. It's also important to consider the problem's constraints. For instance, if the input size can go up to 10 to the power of 5, an algorithm with O(n cubed) complexity will be too slow. Ignoring these bounds can result in solutions that fail for larger datasets. To avoid this, analyze the constraints early on and choose an approach with the appropriate time complexity, such as greedy algorithms or dynamic programming for large inputs. In an interview setting, it's crucial to communicate your thought process clearly. Start by describing the brute force solution to demonstrate your foundational understanding, then explain its inefficiencies before moving to optimized approaches. Highlight the trade-offs involved in your choices, such as time versus space complexity. For instance, if you use dynamic programming, discuss any space optimization strategies you've implemented. Validating your solution with examples is another key step. Walking through small test cases not only shows you understand the algorithm but also demonstrates that you've considered edge cases. If you use recursion, be prepared to explain how you handle the call stack and avoid exceeding its limits. Iterative solutions can sometimes be preferred for scalability, so it's worth discussing why you chose one approach over the other. This problem also connects to other related problems that you might encounter. For example, the longest increasing subsequence problem focuses on finding the maximum length of a subsequence where elements are strictly increasing. Then there's subsets, which involves generating all possible subsets of an array, a similar combinatorial challenge. Combination sum is another related problem, where you use backtracking to identify subsets that sum to a target, often with additional constraints. Finally, partition equals subset sum takes a dynamic programming approach to determine if an array can be divided into two subsets with equal sums. Exploring these problems can deepen your understanding of patterns and techniques applicable to subsequence-related questions. There are several alternative approaches you can consider for solving subsequence problems, each with its own trade-offs. Dynamic programming is a powerful method, as it reduces time complexity by leveraging overlapping subproblems, but it may require additional memory. This approach works well for tasks like finding the longest increasing subsequence. Backtracking, on the other hand, is useful for exploring all possible subsequences, especially when constraints like specific sums are involved. However, it can be slow if pruning is not applied effectively. Greedy algorithms offer faster solutions for problems with simple criteria, such as maximizing a subsequences sum, but they may fail in cases requiring global optimization. For more advanced scenarios, binary search combined with dynamic programming can be a great choice. For instance, it can solve the longest increasing subsequence problem in n log n time, but it's more challenging to implement and debug, making it best suited for performance-critical applications with large inputs. Great job! In this conclusion, we summarized the key aspects of the problem and the solution. Remember the importance of greedy algorithms and hash maps for similar challenges. Thanks for watching, and be sure to practice more problems to strengthen your skills. Don't forget to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!